So, the figure shows a solid made up of 3 parts. The top conical part, the middle cylindrical part, and the semispherical base. The base has a radius R, capital R, with the top a truncated cone with the top radius small r, and the cylindrical part has the height capital H, and the frustrum of the conical part has the vertical height small h, isn't it? Then you've been told to take small r to be 4 centimeters, big R to be 7 centimeters, small h to be 3 centimeters, and capital H to be 10 centimeters. Hence, you determine the total surface area and the volume of the solid in liters, isn't it? Now, when you are going to get the total surface area, you are going to get the surface area of the semispherical base, isn't it? Then the curved surface area of the cylindrical part, isn't it? And the curved surface area of the conical part. Meaning there are 3, there are 4, and the surface area of the top, isn't it? Are you seeing that? Are we together? So for you to get the surface area, the total surface area, there are 4 surface areas here, isn't it? The surface area of the semispherical base, isn't it? Then the curved surface area of the cylindrical part, isn't it? Then the curved surface area of the cone, isn't it? The curved surface area of the cone, then the surface area of the top, isn't it? So let us start with the bottom. We are now on the surface area. So on the surface area, start with the bottom spherical part, isn't it? So the first surface area, we are now looking for the bottom bottom semispherical part. So how do we get the surface area of a semisphere, isn't it? And you know, it is just the curved surface only, isn't it? So how do you get the surface area of a sphere? The surface area of a sphere is, how do you get the curved surface area of a sphere? 4 pi r squared. The surface area of a sphere. How do you get the surface area of a sphere? The volume of a sphere is 4 by 3 pi r cubed, isn't it? And how do we get the surface area of a sphere? It is 4 pi r squared, isn't it? The surface area of a sphere is 4 pi r squared. So the surface area of a sphere is given by 4 pi r squared, isn't it? But this is not our sphere, it is a semisphere, meaning a half of it, isn't it? So it means for a semisphere, it is going to be times a half. And remember the r which is here is big R, isn't it? It is capital R. So it is 4 pi r squared times a half, because it is a half of a sphere, a half of the curved surface of a sphere, isn't it? So what do you get there? You get 2 pi r squared, which is what? Go to the calculator. 2 pi, then r will be given to be, capital R is 7 centimeters, isn't it? 7 centimeters. So what do you get there? 2 pi, 2 centimeters, then is that 7 centimeters squared, r squared, isn't it? So you get it to be 307.88. So you know here you'll be not told to take pi to be this, meaning you just take pi the way it is in the calculator, isn't it? So 307.88 centimeters squared, isn't it? So we have found the surface area of the semispherical bottom, isn't it? Then now what do we want? The curved surface of the cylindrical middle part, isn't it? Are you seeing that? So curved surface of that curved surface of cylinder, or the curved surface of that cylindrical part, isn't it? Now, how do we get the curved surface area of a cylinder? You see, this is a cylinder. If you open it up like this, it's like that circumference is going to be the length, isn't it? Are you seeing? See, if this cylinder when it is closed, isn't it? But if you open it up, see that curved surface here is what you see. When you open it up like this, meaning the circumference becomes the length if you open it up, isn't it? Are you seeing that? Then the height remains the height. So it means the curved surface area is that the circumference times the height. Are you seeing that? And the circumference is 2 pi r, isn't it? Are you seeing that? Are we together? Meaning the circumference times the height, capital H, isn't it? So the circumference is given by 2 pi r, no pi d, because the radius of the cylinder is also capital R, isn't it? So the circumference is 2 pi r, then times the height. Because if you open the circumference, stretch it like this, the circumference becomes the length, isn't it? Times the height. So that gives you the curved surface of the cylindrical part, isn't it? Which is 2 pi, then capital R, you are going to take to be 7 centimeters, isn't it? Then capital H, you are going to take to be 10 centimeters. So, gentlemen, what do we have to be the curved surface of this cylindrical middle part? 439.82 centimeters square, isn't it? Yes, so if this is your cylindrical part like this is the circumference. If you open it up, the circumference becomes the length times height to give you the surface area, isn't it? Good. So we are done with this. Then we want the curved surface of this frustrum of a cone, isn't it? Are you seeing that? Curved surface of a frustrum of a cone. So how do we get that? The curved surface area can write as SA, the curved surface area of that frustrum of a cone, isn't it? How do we get the curved surface area of a cone? It is pi RL, the slant height, isn't it? It is pi R times the slant height. So you cannot get the curved surface of the frustum if you don't have the curved surface of the whole cone. Meaning you have to complete this frustum to be a whole cone. It's when you use the scale factor. Are you seeing that? So this cone, you complete it. So when you complete this cone to be a complete cone, like this, from here, you will complete this to have a complete edge, isn't it? So, from here up to here, you can let it to be small edge, H1, isn't it? Then from here, the whole of this up to this is that is H2. The bigger one is from here up to here is the bigger one. Are you seeing? So the height, the vertical height of the bigger cone will be H2. Then the smaller cone is the vertical height of the smaller cone is this H1. Are you seeing? Are you seeing that? Yeah. Good. So the area you use there, you start with the linear scale factor, isn't it? Linear. So the linear scale factor will be, if you take small r, it is over big R, isn't it? Then you start with small r, then you must also start with small h over big H. And remember the theory of small Are you seeing? Because we want to use this relationship, because we know small r and big R, we use that relationship to give us the linear scale factor. With that relationship, we can now get anything, isn't it? So we use what we know to get what we don't know, isn't it? Then, from there, you will also know if you put the slant height, because we are going to have the slant height is what is going to give us the curve surface here, isn't it? So you can let this bigger slant height from here, from this point, the whole of this point, from here up to here, the whole of that slant height to be L2, isn't it? Are you seeing that? Yes. Then the slant height of the smaller cone from here up to here, you let it to be L. Are you seeing? Because you know the curve surface area of a cone is pi RL, isn't it? So it means we need this slant height. And we can only get those slant heights with the Pythagoras theorem and the scale factor, isn't it? Are you seeing that? So it means if it is small h over that, this one will also be L1 over L, meaning the smaller cone, the radius of the smaller cone over the radius of the bigger cone, isn't it? The height, the vertical height of the smaller coin over the vertical height of the bigger coin, isn't it? Then the slant height of the smaller cone over the slant height of the bigger cone. Remember, the slant height of the bigger cone is starting from here to there, isn't it? And the smaller cone is just from here to there. So can you now get to what you know here? So you have small r is what? 4 centimeters, isn't it? Then it is over big r is what? 7 centimeters. So you see from there, you have the linear scale factor, isn't it? Now you see, you've been given from here to here to be small h, isn't it? Small. So what is h2? If you look at h2 there, what is h2? h2 is that small h plus h1. Because from here to here, you'll be told to take to be h, isn't it? Then from here to here, you say it's h1, isn't it? So it means now the whole of this is h1 plus h. Are you seeing that? Meaning big H is H1 plus, meaning H2 is H plus H1. Are we together there? So go where this H is small h over H2. This small h is H1 over H2. H2 is H plus H1. Then it is equal to the same linear scale factor. Are you seeing what has happened? You know that is not going to help you to get this small h. Because this h you know, from here up to here, this small h, you were told to take it to be 3 centimeters. So you see, we were told to take this small h to be 3 centimeters. Now see, what do you now have there? See, you cross multiply. Yes. See there? So if you cross multiply 7 times small h, you get 7h1 is equal to 4 into 3 plus h1. If you cross multiply. Are we together? Is that okay? So after you've done that, go on. What is now H1? Open that bracket and get me H1. See, here you have 7. H1 is equal to 4 times 3. Then 4 times H1. 4H1, isn't it? So H1 coming this side, you have 7H1 minus 4H1, isn't it? Then you get 3H1 to be equal to 12, isn't it? So what is H1? H1 is 4. So if H1 is 4, what is now H2? See, H2, you can see, it is H plus. See, H2 was H plus H1. Are you seeing? Meaning H2 is, H is, see, H is 3. Now they are together. H is 3. So H which is 3 plus your H1 plus 4, you get H2 to be 7. Are we together? Yes. The same linear scale factor is the same for everything. Is that okay? The linear scale factor is the same for everything. So you see this H1 from here up to here, you found it is 4. And this radius was what? The radius small r was also 4. So you can now get the slant height L1 by using Pythagoras theorem, isn't it? Because that slant height is what we are interested to get the curved surface of a cone. So can you now soon look at that? You are that part. So that part we have. Look here. The small edge here, this is 90 degrees, is 4. We found it is 4, isn't it? Is it? We found it to be 4. Yes, small edge one we found to be 4. So this is edge 1 here we found to be 4, and this was small r, which was also given to be 4, isn't it? So now what is this L1, this land height, L1? See, it's the Pythagoras theorem. So you get L1 is square root of
16.
4 squared plus 4 squared. See, that's the Pythagoras theorem.
Yes.
Square root of 32. 5.66. 5.6. Yeah, 66. No, you do not round it down. 66 what? 5.66 if you round it off.
Yes.
So 5.66 centimeters. So you miss this small L1 is 5.66 centimeters. So it means we can now get L2. Now you don't need L2. The reason being, this is what you do. Once you found the surface area of this smaller cone, you now use the area scale factor to get the surface area of the bigger cone. Are you seeing? Are you seeing what's happening? Then now it is the surface. We are talking about the curved surface. Then it is now the curved surface of the bigger cone minus the curved surface of the smaller cone. Meaning you don't even need to waste your time getting this L2, isn't it? But if you like, you can as well get it. Are we together? If you don't want to use area scale factor, you can still get it without using area scale factor. Okay? Are we together? Now, look at this. We found L1. What is L2? L1 over L2 is 4 over 7. L1 over L2 is 4 over 7. And L1 you found to be 5.66. You substitute it where L1 is, isn't it? Yes. So what is L2? So you cross multiply. 7 times 5.66. 7 times 5.66.
39.62.
39.62 to be equals to L2 times 4 for L2. So that is implying what is L2? So you divide both sides by 4.
Yes.
Isn't it? Yes. If you divide both sides by 4, what is L2? 9.91. So it means this longest land height L2, you found it is 9.991 centimeters, isn't it? But you can as well use it with the Pythagoras theorem because the whole of this length and this r. Are you seeing? This bigger r you are told is what? 7 centimeters. So it should L2 is as well the same as Pythagoras theorem. 7 centimeters square. That is the base, isn't it? Then times the whole of this. Here is 4, and this edge you are told is 3. So 4 plus 3 is 7. So it is 7 square root of 7 squared plus 7 squared. What do you get to be L2 with Pythagoras theorem? You still get approximately the same thing, isn't it? 9.89 like that. Meaning 9.89 is still 9.9 there, isn't it? Are we together? Meaning with Pythagoras theorem, you are getting L2. With the scale factor, you are getting L2. So L2 9.91, you can say that is approximately 10, isn't it? Or you can just say to one decimal places approximately 9.9 centimeters, isn't it? Are we together? So you see, you can use both scale factor and both Pythagoras theorem together because these L's are what we are interested in, isn't it? So we found L1 is 5.66 centimeters, and then the total you found is 9.91, or just 9.9 centimeters, isn't it? Are we together? Now, having found those are now what were important, isn't it? So, what is now the curved surface area? The curved surface area of a cone is to know it is pi RL, isn't it? So here it will be what? The curved surface of the bigger cone minus the curved surface of the smaller cone give you the curved surface of the first term. And that is what we are looking for, isn't it? So the curved surface of the bigger cone will be pi R L2. Are you seeing? See the slant height of the bigger cone is L2. So it is pi R L2 and the radius of the bigger cone is R2. Are we together here? Then it is minus the curved surface of the smaller cone. Are you seeing? The curved surface area of a smaller cone will be what? See pi RL again. Pi, then R of the smaller cone is smaller, isn't it? Then the slant height of the smaller cone is L1. Good. It's L1. The slant height of the smaller cone is L1. So if you work out this, gentlemen, what do you have? Start. This is pi. Then big R you were told is 7 centimeters. Then L2, you found L2 to be 9.9, isn't it? L2 is 9.9 centimeters. Then it is minus pi RL again. Pi times the small r you were told is 3 is 4 centimeters, isn't it? Small r is 4 centimeters. Then L2, L1 you found to be 5.66 centimeters, isn't it? 5.66 centimeters. So what is that curved surface area? What that in the calculator would you get? 146.59 centimeters square, isn't it? Are we together? 146.59 centimeters square. Now, having done that, what is left is this top only, isn't it? See, we formed the surface area of the cylindrical bottom, the surface area of the semispherical bottom, isn't it? Then we found the curved surface area of this cylindrical middle part, isn't it? Then we found the curved surface area of this frustrum of the cone, isn't it? See, what is left is this top, see there? So the surface area of the top, So what is the top surface area? See, that top is a circle. Yes. See there? Yes. The top is a circle. This is the top. It is a circle. So what is the area of a circle? Pi r squared. Because this top is having really a small r. See there? The radius is smaller. So what is pi r squared? That is pi, then small r you were told is 4 centimeters, isn't it? 4 centimeters. So pi r squared. What do you get with the surface area of the top? 50.27 centimeters square. Now you see, you found the surface area of each and every part. So you can see how to handle any problem when you meet such kind of problems in the future, isn't it? You have to handle each and every part independently. And when you have a case of a frustum, you must use the scale factor to determine those lengths, isn't it? Are we together? Because it is a right accord, it's like a right frustum, meaning the slant axes are the same, isn't it? Are we together? Now, what is now the total surface area? Total surface area. Now, the total surface area, that is what we are looking for. You add all the surface area, isn't it? Yes. The surface area of that semispherical bottom, the curved surface area of that cylindrical middle part, then curved surface area of the frustum of the cone part, then the surface area of the top, the circular top, isn't it? So if you add all this surface area, what do you get to the total surface area? This plus this plus this plus this. What is our total surface area? These kind of questions are very important in exam because they are procedural. You can always do them, isn't it? Are we together? Yes. Good. What do you get there? Here we have 944.56. Is that what you have there? 944? Have you confirmed it? 944.56 centimeters? 944.56 centimeters? Yes. Square, you confirm, isn't it? Yes. So that is the total surface area, isn't it? Now after the total surface area, what else do they want? The volume of the solid. So for us to get the volume, we must get the volume of the semispherical bottom, isn't it? Then we must get the volume of the cylindrical middle part, isn't it? Then we must get the volume of the conical top part, isn't it? Are we together? So there are three figures we are determining their volume. Then the total volume we add all of them, isn't it? So let us do that. Let us do that. So start. The first one is the volume of the semispherical bottom, isn't it? So here we are looking for volume of semispherical bottom. Now, this is a semisphere, isn't it? So you start by the volume of a sphere, isn't it? The volume of a sphere is given by 4/3 pi r cube, because this one is using capital R, isn't it? So if it is a semisphere, you are taking a half of the volume of a sphere, isn't it? Are we together? A semisphere is a half of the volume of a sphere. This semispherical bottom, ABC. That semispherical part, its volume is 4/3 pi r cube for a sphere, then you take a half of that volume, isn't it? So you get this one. 4/3 times a half is 2/3 pi, then r cube. And r, you are told, is capital R is 7 centimeters. So 7 centimeters, then cube. If you work out this, what do you get to be the volume of the semispherical bottom? You see why I'm taking my time to handle these cases of volume and surface area. Because they are very easy things, and they are the things I would expect you to concentrate on, okay? Are we together? Yes. So what do you have there? Work it out. 2/3 times 5 times 7 cube. Here we have 7 and 7. 718. 0.38 centimeters cube, isn't it? Are we together? Yes. Good. Then we go to the volume of the cylindrical middle part, isn't it? Yes. Volume of the cylindrical middle part. So how do we get the volume of cylindrical middle part? For you to get the volume of a cylinder, it is the cross-sectional area times height, isn't it? And the cross-sectional area is the area of this circle, isn't it? The cross-sectional area is pi r square, because this cylindrical part is using big R, isn't it? Then times height, and this height you are told is big H, so it is pi r square H. So that is the volume of this cylindrical middle part, isn't it? So if you substitute, what do we have? Pi, then R, the big R you are told is 7 centimeters, isn't it? So pi, 7 centimeters square times big H, you are told to take to be 10 centimeters. This one you are told to take this to be 7 centimeters, small h, you are told to take to be 3 centimeters. In that order, we know everything, isn't it? The big R you are told to take to be 7 centimeters. So the big H is 10 centimeters. So if you work out that, what do you get? 3,000. It is 1530. Yes, 1539.38 centimeters cube. Good. So that is the volume of the cylindrical middle part, isn't it? Then next is the volume of the frustum of the cone, isn't it? See, the top part is this frustum of the cone. Remember, this was just an extension for the scale factor, because you cannot get the volume of a frustum. You must complete the whole of it is when the bigger cone minus the smaller cone to give you the volume of the frustum, isn't it? So the volume of a cone is like, it is some part of a spherical part, isn't it? Meaning if the volume of a sphere was given by pi r squared, then the cone is due by taking a third of that, isn't it? Are we together? Yes. And that can be explained through maybe integration, some kind of, you see how to determine that. So you know volume of conical, the volume of the conical frustum top, isn't it? So this volume, it means you get the volume of the bigger cone minus the volume of the smaller cone, then you remain to the volume of the first arm, isn't it? Are we together? See, the volume of a cone is given by a third pi r squared edge, isn't it? But you check, this bigger cone, what is the radius? Because the bigger cone is starting here and ending, isn't it? So the radius of the bigger cone is bigger, isn't it? And what is the height of the bigger cone? See, the height of the bigger cone is from here up to here, the vertical height, isn't it? Are you seeing? And that height is h. See, from here up here we denoted by h2.
Yes.
So it means this is not h, this is h. That is the volume of the bigger cone, isn't it? Then it is minus the volume of the smaller cone. The smaller cone is now from here up here, isn't it? So volume of the smaller cone will be a third pi r squared h1, because you can see this smaller cone, its radius is small r, isn't it? And its vertical height is h. Are we together? Are we together? The volume we are using the vertical height, isn't it? Just like the case of a cylinder, we were using the vertical height h, capital S, isn't it? Is that okay? Very good. Now, what do you get here? You start substituting. You see, a third. Substitute. We have a third pi, then r squared. So the radius of the cone is capital R, which is 7 centimeters. Then squared. Then it is times h2. We found h2. What did we get h2 to be? We found h2.
7.
h2 was
7.
We found h2 was 7 centimeters, isn't it? Because it was h plus h1, see there? Yes. And h1 we found was 4 centimeters, see there? h2 was 7 centimeters, very good. Then it is minus a third pi, small r. The r we were given to be 4 centimeters, the small r, isn't it? 4. So that is 4 centimeters squared. Then h1 we found from the scale factor to be 4 centimeters, isn't it? Good. So when you work out this, what do you get to be the volume of the first drum? What do you get to be the volume of the first drum? It's the volume of the bigger cone minus the volume of the smaller cone to give us the volume of the first drum part, which is 292.17 centimeters cubed, isn't it? Now what we are now looking for is the total volume, isn't it? The total volume, meaning when you are looking for the volume of this solid, it is the total volume. You add all the volume of each and every part, isn't it? So the total volume is going to be what? Total volume is equal to the volume of the semispherical bottom plus the volume of the cylindrical middle part plus the volume of the conical first drum top, isn't it? So what do you get there? To be the total, this plus this plus this, we get the total volume of the solid, which is 2,549.93 centimeters cube. But you are told to leave this volume now in liters, isn't it? So you know 1 million centimeters cube is 1 liter. So there, because it is 1,000 because 1,000 centimeters cube is 1 liter, isn't it? And 1,000 liters is 1 meter cube. So it means 1 million centimeters cube is 1 meter cube, isn't it? So the liters is in between, isn't it? So 1,000 centimeters cube is equal to 1 liter, isn't it?
Yes.
So if 1,000 centimeters cube is 1 liter, therefore 2,549.93 centimeters cube will be how many liters, isn't it? You cross multiply 2,549.93 times 1 liter divided by 1,000. So what do you get? It will be 2.54993. So that is, if you round up, it is 2.55 liters, isn't it? 2.55 liters. You just use the relationship. If 1000 centimeters cubed is 1 liter, therefore 2549.93 centimeters cubed will be how many liters? Meaning it will be more liters, isn't it? So you just cross multiply that and you get it is the same as 2.55 liters. Are we together? So such kind of questions are very simple and I don't expect you to ignore them when you see them, okay? The only thing that is that they normally have a lot of statement, isn't it? But that lot of statement is what makes them simple, isn't it? Very good. So handle such cases if you come across them.